Let's take a look at a problem where we form a lactone, and this is a problem that's very similar to clicker question number 27 in your notes. So what we start with is carboxylic acid, and then later on in this chain we have an OH group. Now when we put in an acid, such as H2SO4, we know that we have these looking molecules, and these are H+, like that. And what's going to happen in this first step is a pair of electrons on this carbonyl oxygen is going to get protonated. Now with this protonated O on the carbonyl, we're going to have a positive charge on the O. And the rest of the chain for now is the same. Okay, so step 1, protonation. Now in step 2, with this OH and its lone pairs, it sees this carbonyl group, and now this carbon is even more nucleophilic because it wants to push electrons up onto this O so that the positive charge goes away. So step 2 is attack of this O to the carbonyl. Pushes a pair of electrons up. And now this is a ring forming step. So we're going to end up the ring here. Okay, so the bond that formed is this bond right here. Make it bold. That's the new bond. So then this oxygen here is that oxygen there, which is bonded to this carbon, that carbon there, and then so on and so forth. Okay, now right here we just formed a molecule of water in the first step. And water can act as an acid or a base. And in this case, it's going to act as a base. So I'm going to draw that water molecule that we formed. And then if it's going to act as a base, it's going to deprotonate this H right here to get rid of that positive on the O. Okay, now this water became an H3O plus again. And we're left with this structure for the meantime. Okay, so next step is one of these OH groups is going to use a pair of its electrons to become protonated. So it's going to use a pair of electrons to steal an H off of this H3O plus that we just formed. So now we have a water group on this ring. And this OH that we had from before. Okay, water can be happy by itself. So this can easily break away and be fine. And now what the driving force is here to cause that water to leave is a pair of electrons on this OH is going to come down and form a double bond with this carbon. Now this carbon would have too many bonds, so it has to get rid of one, and that's the water. Okay, so there's our base structure, and then now our functional group is going to be a double bond to an O with an H. Okay, and then as we saw here, water left, so we can draw our water down here. Okay, and then the last step should be obvious, and that is deprotonation of this H to get rid of this plus on the carbonyl oxygen. So we get rid of that H. And we're left with acid, so we reform that acid that we started with. And this structure is called a lactone. Here are some more problems from this unit. If you'd like, you can pause the video and work through these, and then we can go through how to solve them afterwards. So let's start with the first one at the top. So we have a benzene ring bonded to a carbon with a double bond to another carbon. And then at the end of the chain is an aldehyde. And if we add in LiALH4 with dilute acid at the end, or in this case just acid, what do you think will happen? Well, LiALH4 is a strong reducing agent, right? So it can reduce carboxylic acids, ketones, aldehydes, but it will not reduce carbon-carbon double bonds. Therefore, we only reduce this aldehyde right here, and the final answer is this. So as you can see, we turned the aldehyde into an OH group, but we preserved this carbon-carbon double bond, and then of course the benzene ring. Okay, now for the next problem, we start with this acyl halide has a chlorine group in place of where normally we would have an OH if it was a carboxylic acid. So this is a carboxylic acid derivative, and then we add in this structure with an O- on it. Now what ends up happening is that this O- will attack the carbonyl carbon. Now when it does that, when this set of electrons attacks this carbon, it pushes up one of these double bonds onto the O. But then, if you remember, if we have a good leaving group on this carbonyl-carbon, the electron pairs can come back down and kick off that good leaving group. In this case, we do have a good leaving group, so that will happen. And then we just have a new bond between this O and the carbonyl-carbon. And it looks like this. So the new bond is right here. And then you have the remainder of that chain bonded to that O still. Okay, for the next problem, try to identify which reaction this is, and you can tell by the reagents that we have here. So this reaction is the Claisen condensation. So we're going to be using this alpha carbon. First, in this reaction, we have to remove one of these alpha hydrogens in order to get a lone pair on this C, and then the reaction proceeds. Now your final product will be this structure right here. And again, if you want to see the Claisen, another example of a Claisen condensation, I did an example in the last video set, so you can go back and view that video. So this part of the molecule is what we have here on the left. So we took away one of these H's, we just have one H now on this carbon, which is the H going up. And then this CH3, we just bent down. Now the new bond that forms is right here. And it just forms from another molecule of the starting material. So two of these come together and form one longer chain. So that's the product from our Claisen condensation. Now in this next problem, we have a benzene ring with a C triple bonded to an N. So let's put in LiALH4 with a water workup. And what we get is this product. So as you can see, all we did here was we reduced our C triple bond N down to just an alkane form, CH2, NH2. Now remember, again, LiALH4 will not reduce carbon-carbon bonds, but it will, and it can reduce these carbon multiple nitrogen bonds. Okay, now next we have this structure again, our acyl halide, and we are also going to put in LiALH4 and dilute acid. So for this problem, remember LiALH4 gives away hydrogens to reduce. So the first thing that happens is a hydrogen will come in, attack this carbonyl, pair of electrons go up onto the O, but then they fall back down to reform the double bond because we can kick off a chlorine. So when we do that, after the first step, we get this H3C bonded to the carbonyl, bonded to an H. Now we just do the normal reduction of a ketone, an aldehyde, because that's what would be left after that first step. And we can add 2 more H's to this carbonyl carbon. One more H to this carbonyl carbon, but then we protonate the O-. So the final product looks like this.